Hey guys, so this is going to be a very comprehensive video about PID controller. We'll be controlling a DC motor, and we'll go over PID and the anti-windup concept, and basically learn how to formulate it inside the Arduino code. We'll use the timer interrupts as well of Arduino, so we can measure time and basically keep track of events, and use that measured time in our Arduino PID controller time step. We're gonna track DC motor position and speed. We'll have a desired predefined trajectory, and we'll have our motor follow that trajectory as close as possible using the PID controller. I'm gonna quickly go over just a basic overview of the code structure. We'll get into the code a little bit later in this video, but I would kind of give you an idea. Like we'll basically be defining our variables and pin numbers for the motors and encoders and other components. Then we'll define some functions, the encoder function to measure RPM and position of the motor, motor driver function where we'll be writing voltage to the motor driver so we can drive the motor accordingly. And we'll also have a timer interrupt function as well to measure time. Then we'll have a setup function, the main setup function. We'll set up the serial to output values. We'll also have to set up our encoder, so we can call that function. Same thing for the motor driver and the timer interrupt. Then we'll have a main loop. This is where the meat of this code is going to be. So we're going to calculate the actual angular speed and the position. We'll also define the trajectory of our speed and position in this loop. And we'll basically calculate the error, the difference between those two. And we'll basically minimize the error using the PID and the anti-windup formulation. And that error will basically go to the voltage, which will be written to the driver that will control the DC motor. So let's go over the PID controller.
So what's PID? PID is basically a proportional integrator and a derivative of the error. And what is error exactly? So let's say if you have a function ut and there's time there, and this is our desired trajectory. In this case, it's a step function, and this is our actual component. Could be a motor or a different sensor or some kind of component trying to follow that trajectory. Let's say it goes and it starts moving away from the red line, and at that point, just for example's sake, we'll say from that point and on the blue line and to the red line, the difference between those 2 points is basically our error. So our controller will basically calculate the error, use that error to move close to the red line, and at every point it will basically calculate the error and try to get closer and closer and closer to the red line, and eventually it will reach a steady state. This is where our gain values for these controllers come into play. So if our gain values are correct or appropriate, then we can reduce the time it takes to get to the steady state and less of a undershoot or overshoot. So let's go over the PID formulation. So let's say we have this UT. This is our controlling function. This is what we're going to control, and we'll have the gain of proportional controller multiplied by the error at point K. So let me just change this T to K as well. So we're talking. We'll do this in discrete time with K index, and we'll add the integrator controller to that. So we'll we'll write the gain for integrator times the integration of the error with respect to t, plus the gain of derivative controller times the derivative of the error. And basically the integration takes the past data, the derivative takes the future data, and the KP is the present. So the proportional controller is pretty simple. You just multiply the gain to the error that you're gonna calculate based on the difference between the actual trajectory and the desired trajectory. Let's look at the integration controller, like how we're gonna integrate the error. So we'll use the trapezoidal method to calculate this. So just overview of trapezoidal method is basically you have a graph here, you have a curve, and let's say there are 2 points on this curve. So this one's k, this one's k minus 1, and the distance between those is delta t. That's our time step. And let's say the integration is basically just the area under the curve. I mean, you can use the rectangular method, basically just finding the highest point and just multiplying by the delta t to find the rectangle. But we're going to use the trapezoidal, so we'll find a slope line from those 2 points and find the average point and multiply by the t to find the little more accurate area under the curve. So the way you're going to write that in Arduino is, let's say you define a variable integration error at point k. So we'll write that equal to integration error k minus 1, the previous error, plus uh, the error at k plus error at k minus 1 over 2. This is basically the average of that red line, and multiply with the delta t to find the area under the curve. And the way you're going to find the derivative controller, we're going to find the derivative of the error is using the backward difference method. There's a whole video on my channel that talks about different differences method, how to use those. Maybe take a look if you get a chance. So you take the error, derivative of the error is basically just the error at point k minus the error at previous point, which is k minus 1, over the time step, the delta t. So this is basically our formulation that we're going to use in the code. That integration equation and this derivative equation. Let's look at the encoder. How we're going to implement this in our code, and what is exactly a control encoder. So we're going to use a DC motor like this with the encoder attached to its back. And this encoder basically has these two sensors here. These are two Hall effect sensors, and there's a magnet on this black disc. And when this shaft rotates, that disc and the magnet rotates around these two sensors and creates square pulses. So there are two sensors that create two square pulses. And this is a little diagram of how this quadrature encoder really works. So if pin A is leading pin B, which means pin A goes up before pin B, that means it's a clockwise rotation. While let's say if pin B goes up before pin A, that means the pulse B is leading pulse A and it creates a counterclockwise rotation. Now, question is, how do we implement this logic in our Arduino code? So we're going to use a external timer interrupts to measure the rotary pulses, because using just the delay function is not going to give you an accurate reading. It's going to be very difficult to solve timing problems without using the external interrupt functions. So let's write this in new Arduino code. So first thing you want to do is you want to define pins. So we have a pin number, pin 2 and pin 3. And also when you're using external interrupts, you have to use pin 2 and pin 3 if you're using Arduino Uno. So if you're using any other Arduino Mega or something, you might have to check the datasheet to figure out what pin to use. So we have defined those two pins, and we also going to define the encoder count. This is something that will be counted every time the shaft is rotated around the sensors, and through that we're going to calculate the position and the RPM of the motor. Let's define this function, the ISR, the interrupt service routine for pin A. So I'm going to adjust my screen a little bit so I can simultaneously write. There you go. Uh, so this is the logic here for pin A. So this is a pin A function. So this interrupt function is only called when there's a change in pin A. So like if it's going from high to low or low to high. So let's say if we have these two lines, these two pulses, one's A and the other one's B, and we're looking at pin A change. So let's say first condition is pin equal to high, so it's switching from low to high. So it's switching at these two places. And we also have to check for pin B condition, and we're saying if pin B is low, there you go. So in this case it's low, not in this case. So that means our rotation is clockwise, so we're going to say our encoder will count positively. So it will increment positively. And if we use the else function, where it means that pin A is switching from it's switching from high to low. It's switching from high to low, so it's switching at this point and this point. And now we gotta also check for pin B status, which is already at low. So it's not at this point, it's on this point right here. So we know the rotation is counterclockwise. So we'll say the encoder is moving to the negative side, so it will be incremented negatively. Similarly, we will have another condition. So if pin B is high and pin A is switching from low to high or high to low, and we'll change the encoder count accordingly. So now we got to make another function for pin B as well. So we have another encoder B function. So in this case, we were looking at pin B switching its state, and also simultaneously checking for pin A. So it's a similar concept as the pin A function. Pin B is similar. So now what we'll do, we'll define our main the void setup function here. So in this, you wanna set up these interrupt pins and the interrupt functions. So you define the pin, you say the pin mode, and you'll use the Arduino built-in input pull-up function, and we'll also define the function for the attach interrupt, which is the external interrupt function. So this is the syntax the Arduino uses. You write digitally to the interrupt, and you write to the pin you define, and then you call the function, and then you look for the change. There are several other things you can look for, rise, or there's few other built-in function that you can use, but in this case we're just gonna look for changes and then call the function. Then we'll define our void main loop function. Uh, we'll define our variable theta, which is the angular position, is equal to the encoder count, and over the 900. I'll explain what 900 is coming from. But let's define the data pin in the beginning of the program. So there's a float variable data, and we can also need a data previous value. This will use that to calculate RPM. So the encoder is basically divided by the 900, and 900 is just the value for count per revolution. So that's the total number count in one revolution, and then the encoder count just gets divided by that. So we get the true angular position. So let's also define RPM in this. So we'll define a float variable RPM, and we'll go to the main loop, and so for now we'll just use the built-in timing function inside the main loop. We'll say t is equal to millis. Milli is the millisecond function, but I'll show you how to measure time using the timer interrupt when we get to the PID. And as I said, that 900 is just a count per revolution, and the encoder count just get divided by it to get the angular position. Now we'll basically define our delta t. So delta t is basically just the t minus the t previous. So, and also the RPM is just the derivative of theta, which is we're using the backward difference method. It's just data minus the previous data over the delta t. The delta t is getting divided by 1000 because I want my delta t to be about 50 milliseconds. So it's just 50 divided by 1000, 50 milliseconds. And times 60 because we're doing a measurement in minute. And at the end of the loop, we have to make sure that data previous gets replaced with the current data value so the loop can go on. And so we get the difference between those. Same thing, we got to do that to time. The time previous gets replaced with t. Oh, I just realized that I forgot to define these two variables, so I'm going to have to go up and let's just define these unsigned long t and t previous. I just initialize t previous to 0. And now what we'll do is we'll write the motor driver function. So basically writing voltage to the motor driver that will run the motor. So in order to do that, first we need to define some pins for the motor. So we say a constant byte pin. We will define a PWM pin because this is not just, we're not just running at high and low. We're running at variable speed. And these are the pins, pin 7 and pin 8. These are the direction of the motor. One will be a positive, the other one will be a negative direction. Now I think we also have to define the voltage variable for the motor, what max voltage we want. So let's define that. So up here we'll say the voltage max is equal to 6 volts. So I'm only using 6 volts, but you can use any. And I also initialize the V equal to 0.1. The initial V 0.1. You can leave it at 0, but I just did it for 0.1. Doesn't make big difference. And now we'll just write our motor driver function just above the setup function. So you see our motor driver has two variables that's gonna, the input variables, the voltage and the voltage max. So we need the voltage max to map the PWM so we can control the speed accordingly. And so this is we're using the 8-bit, it's 8-bit thing, so 255, and that gets mapped to 6 volts. And so there's some logic behind it. So the if condition basically says if V is greater than 0, the direction pin 1 will be high and the other will be low. That means if it's in positive, then it moves to the positive direction. Else, when V is less than 0, it will move in a negative direction, which is the pin 2, which is high, and pin 1, it's low. And when there's no voltage, both pins will be deactivated. And we're just going to write the analog voltage to the motor driver. Once we write the motor function, we have to set up in our void setup function. So we'll set up the pins. We're saying these two pins are output. And we'll go to our main loop and basically say that voltage will be written. And we'll just write voltage to our driver function to run the motor. Alright, let's look at the hardware timer interrupt. So we can use Arduino's clock to measure time, so which will be much more accurate timing events. So Arduino Uno has 3 timers. That's timer 0, timer 1, and timer 2. So timer 2 is 8-bit, timer 1 is 16-bit, and timer 0 is also 8-bit, which is from 0 to 55 in so 655, 35, and 0 to 55. The way we're going to use our time step frequency, which is the delta t, which is our 50 milliseconds, and we're going to actually use the Arduino's clock frequency and basically measure time like that. So since Arduino's microcontroller's frequency is 16 megahertz, we need to calculate something called output compare value. which is equal to the Arduino's clock frequency of 16 megahertz and our delta t frequency, which is just this frequency will be just 1 over time, which is 50 milliseconds, times the prescaler subtracted by 1. So it'll basically just be 16 million over 20 hertz. And the prescaler, you get few choices for prescaler. So your prescaler is 1, 8, 64, 256, and 1024. So whatever prescaler you use, and the and whatever output compare value that you get needs to fit inside one of these timers. So timer 1, 2, or 3, or sorry, timer 0, 1, or 2. So let's use 64 since I've already used it. So the output compare value comes out to be 12499. So this one actually fits. And also one thing is it has to be an integer value. So you cannot use any other prescaler and get a decimal value. That would not work. And this value also fits inside one of these timers bits. So timer 1 range is pretty large, so it fits inside the timer 1 range. So the way you're going to write all this inside the code is you will go to your void setup function. You're going to actually write the CLI command, which basically stops the interrupts. You have to stop the interrupt before you can set up the interrupts, timer interrupts. So the first one, the TCCR1A register is, you gotta set it to 0, same thing you gotta do to 1B. And then you initialize the counter value to 0. And then this is your output compare value. This is your output compare value at 1249 we just calculated. And then you gotta go and set the register 1B using this command. This is from one of the tables. So if you're using that CTC mode, you use that table and you set that value. And this is a prescaler. So this is also from a table. I'll just show you that table. So this table here, if you're using a prescaler, so we're using a 64 prescaler. Oh, that's 256. So if we're using a 64-bit prescaler, so in that case, the CS11, the CS10, these two clocks will be active, and the CS12 will be 0. So we have to make sure that we add this in our code. So we'll go to our code, and here it is. So it's the CS11 and CS10 are active, and the other one's not even listed. And the last one here is you enable the timer compare interrupt, so you have to enable it, and the SEI is just allowing the interrupts back online. So we need to also define a function. We're going to use this built-in compare timer function, and basically we know this function, this event will be happening every 50 milliseconds because we set that timer, and we'll just count every time it happens. And we'll simply use that count in this main loop by using this condition. We'll just say if count is greater than count previous, and I also need to define these values or this variable. So I will go up and let me see. Okay, so I will have to define these two variables first, and I'll just initialize them to 0. So here I'm saying is if count is greater than count previous, I'm just calling the count that event. I know that event is happening at every 50 milliseconds. And so under that if condition, everything will happen at 50 milliseconds. And make sure that you replace the count previous with the new count value. let's go over the PID formulation inside the Arduino code. So first thing what we want to do, we want to define the error variable and also the integration error variable. So we'll also define the error previous, which will be initialized to 0, and same thing for the integration previous value as well. And then what you want to do is you also want to define the desired RPM variable. So this will be our desired RPM trajectory that our motor will follow, and the controller will try to get that as close as possible. And we'll also define the max RPM variable as well. This is already calculated. It's not relevant in terms of finding the proper PID controller gains. It's just to define the trajectory. And this is how we're going to define our trajectory. We're going to say RPMD is equal to RPM max times the sine wave of it. And this is a sine function. This is generally a MATLAB function, but there's no built-in function in Arduino, so we're going to have to create one. And so we'll just create one here as another function as float sine. We'll just take the x value, and it says if x is greater than 0, it returns a positive value. If x is smaller than 0, it returns a negative value. Then we want to calculate the error. So error is just the difference between the desired trajectory minus the actual trajectory. So it's just the RPM desired minus the RPM. And this is the integration variable, the integration error variable. So this is the same thing as what we calculated in the beginning of the video. See the integration error previous, which is just the integration error k minus 1 and plus using the trapezoidal method. And all this error will basically be the summation into a voltage variable. So it'll be Kp times the error, then it'll be the Ki. So I'm gonna have to define those gains as well. So let's just define. I mean, these are I've already calculated them, not calculated them, but found out through trial and error. There is no proper way to calculate these. So all this will control the voltage to the controlling function, and that will be written into the motor driver. And now there's another problem, something called anti-windup. So that happens when the integrated term becomes larger and larger and makes the voltage function go beyond its max voltage. So the system limits of our system is 6 volts, but the integrator term can actually make that voltage term inside the program larger than 6 volts, and that will not allow our RPM to reach stability. Will never be stable. So what we want to do, we want to use these code here saying that if V ever goes over V max, set that V equal to V max, set it to 6 volts, and you change the integration error term is equal to integration previous term. And same thing, you do that for when voltage goes below V minimum, which is -6. I'm going to define that here. So V min is -6. And so as soon as the voltage function goes below -6, our if condition will set it to V minimum. And we also wanted to make sure that at the end of the loop we set these previous values to its current value, and we'll basically write that voltage controlling function into the driver and control the motor like that. And let me just compile this, and but okay, before that, let me just define the serial so I can output some of the values. So I'm going to output these RPM, desired RPM, and also our actual RPM. And let's also output time. So I'm gonna just say serial print count. Count basically just goes integer 1, 2, 3, 4, 5, 6, and you just multiply by 0.05, so we can get the 50 millisecond time step printed. So I wanted to show you the setup. I'm not gonna go detail into how to wire this up. I mean, I think you can find a lot of resources out there that can show how to connect motor driver and encoder and stuff. Um, so here's my motor driver. This is the motor, DC motor with the encoder at its back, and the two Hall effect sensors. And there's a tape here so you can see the revolution. And the power supply is set to 6 volts, so that's our max voltage, supplied voltage. And there's a breadboard, and yeah, I'm using the Arduino Uno in this one, and we'll test these in a minute. I'm going to upload this code now, and we'll run it in the serial plotter too. So the red is our actual RPM, and the orange or yellow, it's our desired RPM. And the blue is just the time. The time is simply increasing linearly. And you can see we're pretty close. The little jittery that you see close to the yellow line, and I mean, you can't do much unless you add some other means to reduce friction. It's following the path very well. There's not much overshoot except the beginning one. The motor is basically oscillating. It's going in different directions at a faster speed. And our motor is following that trajectory very well. Down. So you can even export this monitor and bring that data to your MATLAB or Excel. Just basically see the overall trajectory, and we'll do that in a minute here. I'll just show you the graph because I'm not gonna really plot it. So we got our data for the speed, but if you want to also control the position of the DC motor, all you're gonna do is you're gonna create another variable for data D, a desired trajectory for data, and basically find the error using the desired data minus the actual data. And we're gonna same thing. Voltage is still gonna be our controlling function, and we'll write that into motor driver. And and now I've exported the data from the speed using the serial monitor. I've exported the time step. I've exported the desired RPM and the RPM. So the second column here is the desired RPM, and the last column is the RPM, and the first column is my time step. And then there you go. Since you can plot this in MATLAB, you can see the x-axis is our time, and y is our the RPM. So the blue line is the desired trajectory, and the orange one is our actual one. So there is the initial overshoot there, and I mean, you can change gain values and try to optimize it more. And there is some jitter there, oscillation. That's just due to friction. I mean, you can't really do much about the friction unless you can find a way to reduce the friction there. So that's about it. Yeah, that's PID controller, and hopefully you guys learned something or the video was helpful. And if you guys think that, then please like and subscribe. Thanks.